Welcome to Chapter 7. So in Chapter 7, we're going to do just a little bit of Chapter 7. That's the basic idea of what is a function, because functions and relations are kind of a critical role in a lot of things we do. So to kind of illustrate the idea, let's just talk about what is the definition of a function. Um, a lot of people, we talk about function, it depends on one quantity varying from another quantity. So like your grade is a function of your performance on exams, on other things like that. So it's you have to think about that. It's a way of translating. In fact, our class doesn't use the traditional just percentage, and so translating that function is a little bit different. Functions aren't just algorithms; they often have a lot of other things involved in the idea. So more and more, we're going to talk about what is a function and some key things that are associated with it. So here is a technical definition from your book about what is a function. Namely, a function is takes one set and sends it to another set. And this is where there's a couple things that I do want to like highlight a couple key parts of this because they're really, really important for you to understand this idea. So the first one is the word domain. So the domain is the set from which we are starting from. On the other hand, the codomain, not the range, the codomain is the set we're going to. So if I'm take, for instance, all my inputs, all my possible inputs are my domain. So if that was everyone in the class, that would be the domain would be everyone in the class. The codomain would be where I'm sending the class to. So if I'm sending you onto a grade, assigning a grade, take each person, put it in, and I give out a grade. Well, that codomain could be A, B, C, D. It could be something much bigger, but that's the thing. Sometimes we mix this up, and I'm going to point down here a little bit further down in here, is we mix this up sometimes with range. The range is quite literally, so this is all the details. In other words, what it is, the range is exactly all the things that are hit by the codomain. In other words, they already have an input that goes directly to them, not all the possible ones. So that's a little bit of a difference between the two of them. So we have to understand that idea. Often when we talk about these things, when we write them, we often use this notation again, F colon X arrow Y, meaning the function function F takes X to Y. Also, since remember we have X as an element in here, what we often do sometimes is again, simply write this, or more commonly, F of X, which is pronounced F of X. This is the output when I put X in. That is what it literally means. And it's going to be some Y value, or it should be, otherwise my function's not going to work. And then we have later on something called the inverse image. And the inverse image is essentially if you give me the output, what was the input that got us there? Now, so we have what's sometimes called the pre-image, or that's the input that gets us to Y. And then the inverse image of Y is just that. So the inverse image is what got us there. And here's the key thing, that may or may not be unique. And that's the critical thing for when we talk about if we want to get into onto and so forth. So the idea of functions, a lot of this goes back to a German mathematician known as Dirichlet. Um, it really was developed, and there's a lot more about it. So while this says these definitions are based on some things that they have Dirichlet in the 1800s. Truth is, a lot of this was even worked on before then. It's not that recent. Some of the concepts they've been around, and we've worked on them. But most commonly, if you're doing these, we start off to understand them. We're going to use something called an arrow diagram. And the word arrow diagram is kind of really nice. It's going to look like this. You're going to have two sets. So we have set X over here and set Y over here. And we draw the arrows. If F is going from X to Y, as you can see this little arrow here, then I take every X and I draw it to where it goes. This is a relationship more correctly, this is taking a relationship of where does this x go? Well, this x, as we can see, it goes down to y3. X2 goes up to y1. X3 goes to y3. X4 goes to y4. And we get this list. Now, this is a function. Turns out that this actually is a function because every single two properties have to be true. And I'll write these on the next slide. First, every single one of these x's has an arrow out here. So if we had another x value somehow down here, like an x5, and it did not go somewhere, that would break a function. Okay. So you have to have every x has to have an arrow pointing to something in y. And two, no element over here has two different arrows. So in other words, again, I couldn't have, I'm going to add an extra arrow. What if x1 also had an arrow that went over here to y1? In that case, if x2 had both of those, that's a major problem. We don't like that. So again, the two properties that we need is that every x value has to have an arrow pointing to something in y, and every x element can have only one arrow, exactly one arrow, cannot have two arrows unless they go to the same instance. So you could have two arrows, but they just have to go to the same spot. And then it's kind of like, why did I do that? That doesn't make any sense. So let's look at some more examples to kind of understand these. So here are three different arrow diagrams. I want you to look at these and ask the question, which of these are functions? Why or why not? So go ahead and pause the video. A, B, and C, which are functions? All right, so hopefully you did that. And you should have found out that this first one, this is not a function. And the reason for that is because B doesn't have anything assigned to it. What about our second function? Well, it is also not a function. And the reason being C. Notice it goes to both 2 and 3. It cannot have two different outputs. But this last one, it is a function. Now, another example, just to illustrate this idea and to help you kind of understand what's going on, I explain this as what I call the vending machine example. Functions are vending machines. So in this first example that we had right here, it's broken because we imagine these are all the buttons I push and these are the things I get out. In this one, I could press the B button and I get nothing out. So therefore it's not working. In this one, I press the C button and I could get number 2 or I could get number 3 or I could get both. Now, some of you might be like, sweet, 2 for 1. That's a great thing. No, if I'm building a vending machine, I want it to build and kick out only one thing. It doesn't mean it has to kick out every possible selection because these are the only things that it has in its repertoire. So that's the idea over here. This is how functions kind of work. And also notice over here, this is still a function, even though A and C both go to 3. So the difference is, are all these things going to something? And secondly, do they have more than one arrow going out to different things? All right, so let's continue on with some more examples. All right, so here's another one. Let's consider this one where I have X is ABC and my Y is 1, 2, 3, 4. Now, again, we don't have to use X and Y as the names of our sets. We just commonly do that because that's what a lot of people like. Again, and also Deerschley, that's what he liked to use. That's why we use it. But we can use whatever we want. So let me ask you a couple of questions about this set. What is the domain and what is the codomain? Well, the domain of this set would be all of these values in this set right here. So ABC, that would be all of the domain. Y would be the codomain, so that'd be all of the things over here. Now let me ask, I'm going to write these down to make this next one a little bit more clear. What is, so I want you to figure these out. Can you tell me what f of A is? Or f of B? Or f of C? I want you to look at that real quick and think, what are they? Well, f of A would be 2 because that's my output. F of B would be 4 and f of C would be 2. So we have this right here. Interesting enough, then, what is the range? Let me ask you now a new question. What's the range of f? Now remember, that's going to be a set. It's going to be a set of all the things that are actually hit, which is only the set 2, 4. So this is the range, but this over here is the codomain. Again, do not be deceived by that. That's not something that's often is misunderstood about this idea between all these things. All right, let's ask a couple more questions. So let's take C. Is this an inverse image of 2? The answer to that would be yes, because C goes to 2. So if I was trying to go backwards, that's what it would give me. What if I asked another question of what is the inverse image of 1? Well, the answer is it does not exist. And that's because 1 doesn't have anything going to it. It's possible that this function could work more if I had more x's or other things like that. It just doesn't happen to have it. And last, while we do arrow diagrams like this, another way that we can do this is we can rewrite them as an ordered pairs. So remember, we've talked about ordered pairs before. And so we're actually going to create a set pairs of numbers or pairs of values. So I do A and A goes to 2. I do B and B goes to 4. I do C and C goes to 2. So this would be the ordered pairs for this particular thing. And we like that sometimes because it allows us to really look at it and organize it in different ways. So this arrow image is one way to attack this. Another way is to do this ordered pairs. All right, let's look at some more examples. So one of the other things we're going to move on to, before I do another example, I want to talk about this theorem. It's called the test for function equality. In other words, if I have two functions, f and g, and they both go from x to y, they're equivalent. We call the functions equivalent only if when the inputs are identical, the outputs are identical. So in other words, they both have the same domain. They have to have the same domain if their outputs turn out to be the same thing. And this is kind of a critical idea for us to understand. So let's look at some examples. So here we have a function f, which goes from the real numbers to the real numbers, and g goes from the real numbers to the real numbers. We're going to find f plus g is going from real numbers to real numbers, and g plus f is going real numbers to real numbers. The question is, are these functions the same? And they are, and you don't even need numbers to realize this. It's because f plus g equals f of x plus g of x. And these are the same. And since adding real numbers can be added in any order, it doesn't really matter. But that's only true because that's a function that we have with real numbers. So we can add them in any order. For all of you that are curious, that does not always work for every number system. And there's a lot of things we cannot do in different orders, which makes this that much more challenging. So we have to be extremely careful and kind of work on different ideas and approach them to understand them just how much more they can operate. So let's continue on our functions and let's look at a few more things. There's a lot of different functions we can look at. So let's just look at a few different examples. So the first function, that type of function we're going to look at is called the identity function. Some consider this the most boring function in the world because the identity function, it's going to take any input and give it right back. So notice it's a function that literally goes from x to x, and it's just going to kick back. And some of you are like, why do I like this? Well, we like that sometimes because no matter what I put in, I get out. So if I do if I do the identity function of a to the k sub a I j, which you don't need to even know what this is most likely an element of I mean, there's all sorts of superscripts and subscripts. This has a Greek letter, gamma of z. Again, what is that? Well, you don't know what that is because it doesn't really matter because it's just going to give them right back. So the identity function does not even require us to know what we're doing with. It just gives it back. Let's look at a different function that we actually already looked at, and I mentioned it before when we dealt with it. Sequences. The truth is sequences are functions because each input corresponds to a specific index. So the input is the index, the domain is the index, and the output is whatever it is. So for this particular function, 0 goes to 1 because that's the 0 index. 1 goes to negative 1/2. 2 goes to 1/3. 3 goes to negative 1/4. 4 goes to 1/5. And n goes to negative 1 to the n over n plus 1. We can take this and we can then think about, okay, what's my domain? Well, my domain, remember, is all of the natural numbers, because they start at 0, going on. So that's all the natural numbers. And the output in this case actually is going to be real numbers. And so we can say that this is what it is and define as f sub n in this way. So we have all these things to kind of illustrate and work through all this idea. So we can build on this. Let's look at and from here we can even still define it a little bit more, and then we just input and get the same idea right back. All right, so we have lots of ways to define this. Notice this one's a little bit different. So this was n plus 1, and this is n. And this one, it's very similar, but the denominator is just n. This is n plus 1. But if this starts at 1, you get the exact same sequence, even though this, again, remember we talked about this when we did sequences. They can start at slightly different indexes, and you can still end up with the same thing. All right, so let's talk about the power set. We did the power set with sets. Well, that denotes all the subsets. We're going to find the function that takes the power sets to an integer. Specifically, it's going to give me the number of elements in that subset. So the way to look at this, A, B, C, all the subsets are going to be the empty set, A, B, C, AB, AC, BC, and ABC. So remember, these are all the subsets of the set ABC. But notice they only correspond to these 3 values here. Sorry, 4 values, 0, 1, 2, 3, with the empty set going to 0 because that's its cardinality. A, B, and C have a cardinality of 1, so they go to 1. Remember, this thing right here, number of elements, is cardinality. Often we illustrate this with bars around the X to illustrate the same idea. So, but one of the reasons it's sometimes confusing is because that for cardinality, and also when we start talking about natural absolute value, sometimes we get those mixed up a little bit. All right, let's look at another one. So what about here? What does this mean? Well, this is what's called a Cartesian product. So in other words, I'm going to have 2 inputs. I'm going to have an input A and input B, and I'm going to multiply them together to give me my output. So that's literally what this is going to do. Whereas this one has an input and it kicks out an ordered pair as well. These Cartesian products, the way these work, where M is just the multiplication function and R is reflection, meaning the A becomes negative, B stays the same. So let's come here and let's try these things. If I'm just doing this, executing M on these things right here, what would A, B, and C be? Well, this first one for A, this is just going to be -1 times -1 or just 1. Our next one would be 1/2 times 1/2, which is 1/4. And this one, last but not least, would be square root of 2, square root of 2, which happen. Oh, that's a multiplication. Let me get my eraser and change that real quick. That's my error. And so that would be 2. What about these? The reflection, remember, is you just switch the order. So this is going to give me an ordered pair, -2, 5. And this is going to give me 2, 5. So the idea here is I want you to be comfortable because we have multiple functions where we go back and forth from ordered pairs to non-ordered pairs and so forth. And you can think about this if you're creating a function in a computer program or something else, you could start with single inputs and end up with multiple outputs, or vice versa. There's lots of different functions that we define even in computer programming. It's very common to define a function. What is a function? It has to have a defined. I put in input, it better give me the same output every single time. Otherwise, we're going to have a slight problem. Now, another common function that's out there is the log function. And again, many of you, well, you should have learned this. So the log function is a way to work with bases and so forth. So if I asked you this first question here, what is log base 3 of 9? What I'm really asking is 3 to what power is equal to 9? And so this one would be 2. Because again, I'm asking the question, it's the same thing as 3 to what power equals 9? And this one is 2 to what power equals 1/2? Well, going back again to algebra, that's -1. This would be 0 because 10 to the 0 power equals 1. Now, this is an interesting one. What's log 2 of 2 to the m? So it's 2 to what power equals 2 to the m? Well, obviously that is m. And that's kind of where it gets kind of cool. And then we get this one right here. And this is where gets kind of fancy and weird. And this actually turns out to be simply m, because log base 2, this and raising it to the 2 power are inverse functions of each other. They undo each other and they kind of get us out of that situation. And so again, here are all those nicely written up. All right, let's do one last example to help you illustrate this. And that is string functions. So I can have a function that essentially gives me a string of whatever characters. These could be a binary string with zeros and ones, could be much more complex. And these are the things that we can kind of build on and use. And often this is actually used when we're transmitting information, is that we want to create them. And we want to have it so that we can read information and so forth. These are all functions where I can have some kind of word, which is just a string of letters and so forth. All right, I hope that helps. Good luck. Let me know what questions you have.